Hello and welcome everybody. We're very glad that you could join us today. There's a number of webinars that are available to you, and we're glad that you decided to be with us today for the ACC Knowledge Series. Before we begin, I'd like to um, request you all to download the Concrete Club mobile app onto your phone to be able to utilize it and to be able to fully use the recordings and the content that we will be pasting from this particular session onto the mobile app, and you will be able to sort of share your questions and get them answered on that app as well. So with that having been said, we are going to introduce you to this new session. We'd like for all of you to share with us if you're having any trouble with the video or the audio in the chat box. Leave us a message there and we will try and get that addressed. If you're having any trouble with hearing any of the panelists or with being able to see the slides that are being presented. That being said, a few words of how we are going to proceed today. We would like for each one of you to be able to interact with Mr. Tandon today, and that's why he's here and he's given us his precious time. But the way to pose your questions is really to put them in the question answer section and in the question answer section only. And the reason why we say that is because we don't want for your precious questions to get lost in the chat session where it might be difficult to keep track of some of these things. So please feel free to put your question answers and in the Q&A session, use it wisely, especially only and only for your Q&A, right? Already going forward, I see it being utilized, but I would say continue to use it for the Q&A section only. So moving forward, this is how our session today is going to proceed. We would like to tell you about what the ACC Knowledge Series is. The ACC Knowledge Series is a series of webinars that we started, especially given the current circumstances. ACC has been since 1936 engaging with engineers, with the architects on the topics, on different topics of construction, on materials, on technologies. And we've been working with the sole purpose of improving improving the building construction practices, something that we have been producing as propriety. Things are the Indian Concrete Journal and the Concrete Club app, where we talk about better building practices. And this is an advocacy firm and this is an advocacy platform that we use to be able to get you to talk about your great projects and the work that you're doing in that field. We do focus on what is a good building practice for the country, what promotes good workmanship practices, what promotes economical or affordability, what promotes sustainability, and that and much more in that whole umbrella of better building practices. And that's what the ACC Knowledge Series is now taking to a webinar platform, and we should be on a regular basis bringing these to you. So I would say with your local ACC officers and with the different digital platforms we are now using to reach out to you, keep abreast with knowledge of when these events are happening, and we do invite you to participate in them as enthusiastically as you can. So with that, I would like to invite Muin to please introduce the topic for today and as well the speaker that we have. And we are very privileged and we thank you, Mr. Tandon, for joining us today. And over to you, Muin.
Yeah, thanks, Priyanka. And good morning to all. I once again welcome Professor Mahesh Tandon. It's our honor, really, it's an honor by heart, I'm saying, to, host a lecture which is taken by Mr. Tandon. Because since the childhood, we were in the college days, we are hearing the name of Mr. Mahesh Tandon as one of the, the topmost structural consultant of the country. Apart from Mr. Tandon, I'll also welcome all the participants who are from different, variants of the civil engineering professionals, including consultants, architects, engineers, and fellow members of Indian Concrete Institute, Consulting Engineering Association, Association of Consulting Civil Engineering Engineers, India Institution of Engineers, and all other associations, technical groups, academic groups, and my friends, my colleagues. I'd like to thank my colleagues from the Indian Concrete Institute of Nagpur chapter, Mr. Manoj Kavalkar and all. They have also, tried and, in arranging and organizing this session. So I thanks. Always they are supportive. A knowledge series Priyanka has already briefed about. So this is a new way of learning, and what we are finding that all of our engineers, consultants, and all professionals, they have they have adapted very fast to this new way of learning. And each and every seminar we are doing, we are finding a good response. There may be some or minor technical glitches which may happen because there is internet, there is a load on internet, so we all need to bear with it. As far as Professor Tandon is concerned, he doesn't need any introduction, but just to give some highlights, uh, Mr. Tandon is a basically he is not a national but an international personality, and he has designed a lot of structures uh, under his the firm name is Mahesh the Tandon Consultants Private Limited. He is a civil engineering graduate from the Roorkee Institute, from the Roorkee University in 1965. He is MS in civil engineering from University of Hawaii, US. He has also done diploma for civil engineering intercultural living from Hawaii and PG in business management. Professor Tandon has to his credit major design projects in pre-stressed concrete, reinforced concrete, and structural steel in India and abroad, including major bridges, long span roofs, tall buildings, and monumental structures. Here, Tandon Sahab, I would just like to, for your knowledge, I was receiving a lot of mails and messages from our fellow engineers that they asked me why you are not keeping the session on bridges, because Mr. Tandon, he's what I will say, he is the kind of father of designing of bridges in India. So I told them that this is a topic which normally we always hear from Mr. Tandon. So this is a new thing, a little bit comparatively. So as far as bridges is concerned, we will definitely plan. We will discuss with you about the topic in coming future. So, Mr. Tandon's structures are described as highly creative, futuristic, aesthetic, environmentally sensitive, and innovative. He has spearheaded the development of many codes of practice on concrete and bridges structures. He had been a distinguished visiting professor at IIT Kanpur, Roorkee, and now at Gandhinagar. Uh, Apart from being the uh, pioneer in various structures he has designed, he has also won the several awards and accolades for his contribution. He is also a fellow member of all the major professional organizations which are related to the engineers. Professor Tandon has been in yeah. So apart from this, his special area of interest is motivating the next generation to adopt civil engineering as their profession and vocation of life. Uh, I mean, there is a complete list of 81 pages of the CV. I think it will take 2 to 3 hours in talking about Professor Tandon. So I'll not take that much time. We all know Mr. Tandon, and we all welcome him once again in this webinar. Today's topic is, we have already given the key points. It is tall, super tall, and mega tall structures. In India also, we are now seeing not only in the metros like Mumbai and Delhi and Bangalore or Hyderabad, there are even in the B class cities also there are lot of high rise structures which are coming up, and there are lot many questions which generally come into mind related to what is basically the definition of the different of this tall, super tall, mega tall structures, historical perspective and inspirations, structural systems, what will be the structural systems for concrete and steel in these tall structures, and how to build the synergy between the architecture and structure, and current status and road for future. These are the major points which Professor Tandon will be covering in this presentation. So I once again welcome Professor Tandon as well as all our fellow engineers and architects and consultants. Over to Mr. Tandon. Thank you, sir.
Yes.
Hello?
Yes.
You can see. Okay, this is the part one, which is the first part. And I have about 25 odd slides and whatever time it takes. I'd like to say in the beginning itself that 70 million people per year move to cities. 70% of the world's projected 9 billion population will be living in urban areas by the year 2050. Tall buildings may provide the only solution for the built urban environment. There are many friends that I have discussed this with, and many architects don't agree with it also. But anyway, this is one of the solutions, certainly. So the two parts, I have made it simple to understand what they are. And the first part we'll discuss about the definitions of these three words. We will see the inspirations and historical perspective. And of course, we will see the structural systems for concrete and steel. The Council for Tall Buildings and Urban Habitat has given the classification as you see on your screen now, based on height. 50 meters is tall, 300 meters is super tall, and 600 meters is mega tall. The last mega tall definition has come only after Burj Khalifa building in Dubai. And in 1890, surprisingly, the buildings over 10 stories were considered to be very tall. There is an IS code which has been published by 16700 just 2 years ago. And it is on concrete buildings, and it covers the height range of 50 to 250 meters, all the design aspects. But if you look at tracing the history of the skyscraper, you find out how the immediate past always provided inspiration for the next advancement. This you can see in the present slide. Are you able to see the full slide?
Yes, sir. We are able to see.
Okay. So if you see this carefully now, how the heights of the buildings have increased over the time, and at the bottom you see every time what is the jump made. For example, here it is 25 meters, then it is 10 meters, 57 meters, and the last Burj Khalifa building in Dubai, it's 299 meters is the jump. So the Council for Tall Buildings and Urban Habitat had to think of another definition altogether, because this was not going in the way that it was planned. So let us look at the history and the inspirations which have provided for, tall buildings really into the present attention. So who provided these inspirations? The first was Elisha Otis. I don't know whether you heard of Otis, but this is the same elevator there is also a company called Otis. It's 1850 that he invented the elevator, which could go up and down safely. Then there is the Empire State Building, where the architects and structural engineers, you can see their names here, which was the inspiration for a long period of time. And then the architect Frank Lloyd Wright in 1957, he visualized a mile-high building which could be a city, or at least a mini city. And structural engineer Lynn S. Beadle, he formed the Council for Tall Buildings and Urban Habitat. And to him goes the credit for at least classifying buildings, saying what is tall or not so tall, how to measure the tall building. Are you going to measure, for example, the antenna, which is on top of all buildings or not? Will that be a part of the building? Where do you measure the building from? Is it from the ground level, or is it from the first level that when you step into the building? All these complicated matters were at least thought of, discussed, and then finally put as rules and regulations for how to measure the height of the buildings. There was a structural engineer, Fazlur Khan, a Bangladeshi, who changed the whole aspect of structural systems that are to be used for tall buildings. As a matter of fact, if you see the buildings of today, especially in America and many other parts of the world which he designed, they are totally different from whatever existed before that. And now, of course, more and more people are following his systems even till today. This is Otis, and he's giving a demonstration of the safety brake, because people said that this thing goes up and down, but it is not very safe. It doesn't sound very safe. So he made a demonstration standing there himself at the New York World's Fair in 1854, and at that time there was there was no electricity or something like that by which you could move the lifts up and down. It was done by steam powered engines. So he demonstrated that this is a safe thing to do. And I think that this really started the thinking about tall buildings, that you can go and reach there in a short period of time. The Empire State Building took only 1 year and 45 days to build. In January 1930, the excavation began, and in March 1930, I think this should read 1931. It can't be, it has to be 1 year and 45 days. The construction began with 3,000 workers building 4.5 floors per week. And at completion, it became the tallest building in the world. On 1st May, the President Hoover, who was at that time was the president, he officially opened the building by pressing a button in Washington. Even at that time, this remote things were possible. So it has got 102 stories and 443 meters tall. And it is remarkable that at that time also it could be built in just over a year, 1 year and 45 days. We are finding that these type of buildings, even today, we are taking years to build. It may be 3, 4, 5 years before you can reach that type of a height as far as buildings are concerned. Frank Lloyd Wright, the famous American architect and a favorite of many, many architects across the world, he is putting the finishing touches to his mile-high building, as you can see, and he's written quite a lot about it in his book called Building a Testament, which was published in 1957. So there were no printers, whether laser or any other type. There was only your pencil paper and your brain by which you could draw. And here you can see the finishing touches of the building, which was so tall, and to see it to at least some detail, he is putting the finishing touches to it, and you can see how the paper is even hanging down from the table. So the dream of a mile-high building, which is, let us say, 1,600 meters tall, it is still unrealized. We don't have any building which has reached that height. A kilometer high building, yes, it's under construction, and the completion was supposed to be in 2019, but now I think it is delayed by at least a couple of years. So it may be maybe in the coming couple of years it will be finished. And then you have the present day record, which is an actual building which has been constructed, which is 828 meters. So we are getting there, but at the moment we are just 828 meters. Let's talk about Fazlur Khan, the famous engineer from Bangladesh. He ushered in a renaissance in skyscraper construction during the second half of the 20th century by introducing the tube concept of structure. Of course, he did many things, but it is the tube concept of the structure which uh, has grabbed the imagination of at least the common man. On April 3, 2017, Fazlur Khan was on the Google Doodle, as they call it, on the front page. I think perhaps the only structural engineers who's made it to that level of being famous. And the first example of this tube building was the 43-storied DeWitt Tower, which you can see on your left-hand side. And there are many special issues about this, and we will talk about those. You can see these diagonals which are running across the full height of the building. So what were his main contributions as far as structural engineering is concerned, and as far as tall buildings are concerned? Firstly, the frame, which means, we normally have column beams, and we have the shear wall. That is not the only option that you have for tall buildings. And steel is not the only option. This was particularly so in the US, because they couldn't think of concrete going so high. They didn't even know how to pump concrete to that level. So he also drew some structural system charts for steel and concrete buildings, separate ones, which I will just show you. And the main contribution, I think, that he has done, which has changed the architecture of the building also, is that you push the structure to the outer periphery of the building, providing unobstructed column-free space in the interior of the building. I think this is something which is the column, the architects don't like the word column mentioned in their presence. So this is the guy who gave you an option. As you can see in this sketch, you have got on the outer periphery the structural system. You've got only the core in the middle, and there is no column or anything like that in the middle. So it is something that is completely column free. So all of it is utilized or utilizable. And you can see here, this is the core which actually houses the lifts. You have to have lifts before you can go up. And of course, all the services and utilities, they are all housed here. And from the core to the outer periphery, you got only beams which can span across this length, and no columns. This is some of the pictures that he drew. As you can see, once you are beyond, let us say, about 40 stories height, you don't have to go into this framed system at all. Frames and column beam system, you can forget about them. Once you have crossed 40 stories, he had separate ones for the systems for the concrete and steel, because the materials are basically different. But this formed the basis, and I think it is still forming the basis for tall buildings. as to how to design them and make them economical. This is something which Som, which is the company that he worked for in the US, Skidmore, Owens, and Merrill, they have made this chart again and looks quite nice, all color. Let's talk about some of his buildings. You know, the Empire State Building or the Chase Manhattan Bank buildings, constructed one in the 30s and one in the 60s, they consume 275 kilogram of steel per square meter. The John Hancock Center, which was made in 1965, designed by Fazlur Khan, had only 145 kilogram per square meter of steel, which means he reduced the consumption of steel to half by the various systems that he has adopted. So you can see here it is a trussed system. You still have, of course, the columns closely spaced, fairly closely spaced, and you have a truss. So it is a truss, and which engineers understand very well, but I think even the normal people must be understanding it well, that if you want to span a certain length and you want to make it in steel, let us say once you go beyond 40-50 meters, you make it in trusses. So here he has put the truss on the outer side of the building. And Willis Tower, which he engineered, was the bundled tube. By bundled tube, you can see here there are several tubes. Tubes, incidentally, are not only round. They can also be square, they can be rectangular. So bundled tube means that there are a number of them. You can see them here. And we will talk about, when we talk about the forces and the wind forces in particular, what is the advantage of doing that? So up to 40 stories, as per Fazlur Khan's imagination, he said that you can still have the frame shear wall kind of a system. But the great thing was that in the very early, somewhere in the early 60s or late 50s, he said that if you combine, you see the behavior of these two elements. The shear wall seems to deflect more at the top, but very little at the bottom. And just the opposite happens with the frame. So if you combine the behavior of these two, that means you put some kind of a link between these two, you will have the benefit of both the types of behavior. So up to 40 stories, as per him, it was still okay to do this type of a thing. And this shows you how the forces interact. I mean, here you can see the shear wall is actually being restrained by the frame, and at the bottom you can see it is the shear wall which is being restrained again by the frame. So it depends on whether you are talking about the frame or the shear wall, but they are compatible, and the final deflections that you get at the top are reduced tremendously. Not only deflections, bending moment, shears, all that are reduced tremendously when you combine the two. One of his early buildings, which are still the shear wall frame building, he has not yet taken out the structure completely, was this Brunswick building, which is 35 stories high. And you can see at that time, and even now, as a matter of fact, if you go to New York, most of the buildings, they don't have anything at the bottom, no structure, no obstruction. That is how they want it. They have a huge 8-meter deep transfer girder here, which is taking the entire weight of the building, which is whatever is transferred on the outer side. So it's a amazing thing to see. The guy was not worried about uh, the earthquake being it's not the structure not being really what we think of should be adopted for earthquake resistant structures. You can still do it, but it takes a lot of brains. And here you can see how the transfer is taking place from the all these um, uniformly distributed load, more or less, is finally distributed only to 4 columns in the at the bottom. Now let's go to the next uh, height, which is 40 to 80 stories building. Now there he tried to put the structure on the outside, but what he found was that there is a shear lag. Shear lag is that if you have a wind force in this direction, the most of the forces go here and on the other side, and these are not participating really as far as the wind forces are concerned. Only a very small part perhaps which is very close to it, as you can see here, and the rest of it is not participating really for this. So he had to find a solution for this eventually. And how to eliminate shear lag is why he first made the buildings with trusses on the outer side, because this way you can make sure that all the sides, your structure is located on the periphery, but all the entire periphery will work when you have the wind forces acting. Now you can see he applied that same idea to steel buildings as well as to concrete buildings. There is no difference in the principle, and he was equally comfortable with both of these, concrete as well as steel. This is the John Hancock Center, Chicago, 1965. Perhaps the first 100-story buildings, but this was made in steel. And the last building that he made was the 3rd Avenue, New York building, which is only 49 stories, 170 meters tall. And the last building that he designed really shows you he was really very fond of concrete, more than steel. But in America in those days, you couldn't prefer concrete over steel. Even the cost benefit analysis didn't really go in favor of concrete. Later on it did, but at that time it didn't. So his last building, of course, was in steel, like I mentioned. This is what his true love was, concrete. So once you go beyond 100 stories, what should you do? What he suggested was you do a tube in tube, which means that you have a tube on the outer face, as you can see here, and you have a tube in the middle, and you join the two so that they behave together. The tube, the one at the center, this is really the core which houses the services, utilities, lifts, etc. And it is really the outer side where it takes not only the part of the gravity load, but also takes all the lateral forces that go on to the building. Once you go much beyond 100-meter stories, he suggested a bundle tube, which means that you bundle a number of tubes together, and the structural system provides greater strength and stability, since the configuration of tubes can disrupt the wind flow around the building. As a matter of fact, even if you see the Burj, building of today, the idea has been taken about a bundled tube. As you can see here, for example, you can have any kind of configuration. You can have short, tall buildings. You can have buildings of the same height, all bundled together. This is of great help as far as mitigating the lateral forces, which is basically wind and earthquake, are concerned. Then he also invented, as you can see here, one of his buildings. He put a truss at the top and at the middle, for example. So if you have a number of these throughout the height of the building, and suspend part of the load from there, it is extremely efficient, because the bending moment, instead of going down in the shape like that, where you'll reach somewhere here, you have only reached here, because this is a sort of a collector, you can say. So this response without outrigger and with outrigger, you can see what the tremendous difference it made. So this is another thing that he made, that you put trusses even along the height of the building, not only on the outer side, which you have been seeing so far. So this is called the outrigger belt system. You can, instead of trusses, you can also put 1 floor height girders, and this is equally good. Here's another example of outrigger belt system. As you can see from here, this is the these are all outriggers that you see, 1, 2, 3, 4, and 4 on the other side. So you got 8 outriggers which are holding up part of the load and transferring it to the trusses. This is what it looks like. Okay, so last slide. If you make buildings taller, what is the price you are paying? This amazing graph that he made is that if you had an ideal structure which is insulated from wind and earthquake, there's no lateral load, then as you can see, whether it is a 10-storied building or it is a 100-storied building, there is practically no difference. Maybe 20-30% is all that you have to pay extra if you insulate it from the lateral loads. But the moment you take them into account, the lateral loads, that means that the lateral loads are making you go from here to here, which is almost 5 times, for example, at 100 stories. So this is because of the lateral loads which come into play, unlike just the gravity loads which were in play, for shorter buildings, or if you had just insulated it, if it was at all possible. So you can see the price that you are paying for making the building high. It is quite a lot. Okay, this is the end of part 1. Thank you. And I think now Moin and Priyanka will take over, and let's see where we go.
Sir, now we have question answer session. So one question, sir, it is very relevant that Mr. Mukund Joshi wants to know, after COVID-19 pandemic, will architectural revolution will be necessary so that the congested living is avoided? Just a minute, I just lost that question. Yeah,
I understand it.
Yeah. So congested living is safe in future pandemic. Yeah.
You look at it this way. Supposing you are living in a tall building, and one person in that tall building is infected. This entire building, tall as it may be, you are going to be under lockdown. You are going to be in the red zone. So it has got good points and bad points. So don't think that this is a recipe for future pandemics. It may not be.
And we are seeing that if there is any such issue, the whole colony or whole society is being putting under quarantine. I mean, they have to be
Yes.
put under quarantine. So anyway, there is one question from Mr. Dharmendra Kumar that why the occupied floor of Burj Khalifa is still the height of 585 meter, not till its actual height of 826 meter.
You see, there is 608 meters, as far as I remember, which is in concrete. The rest of the 80 meters is in steel. It's an antenna. So with the new norms, new means that they were changed about 10 years ago, the entire height of the building is to be taken into account when we talk about the height of a building. It's not only the part which is livable or occupiable. It's a complete height. So that is why it is 686 meters, and the concrete part is only 604 meters or something like that, as I remember.
586 meter is the occupied height. What is
Occupied height, yes.
So the next question is, yeah, from Mr. Vikram saying that what about the non-linear analysis of tall structures? Is there any Indian standard code for it?
I think non-linear analysis, we have to get into it, although I would say that it is still in the very infant stages as to how to go about it. We have got a lot of softwares like, you can do a pushover analysis, which is a kind of a non-linear analysis. But we are talking about, these are all very simplified things. When you talk about tall buildings, it has to be dynamic, it has to be inelastic. Both these come into the picture. No longer static analysis. You can do the static analysis by all means, but that is the future. And I think with the youngsters that I see, they are more interested and more capable on computers than all of us old people are. They will develop these techniques as to how to go about it. And new codes that are going to come, they are going to have this, they are going to have a performance-based design, because all this is really, why are we doing all these analyses and things like that? It is really to ensure a certain performance when you have a catastrophic event. For example, if you have an earthquake or you have a typhoon, now what is it that you want from it? Do you want that everything should be safe, or you are willing to accept a certain amount of damage and certain amount of damage to the structure or to the non-structural items? So all these questions arise when you talk about a performance-based design. That is going to be the next code which is being worked on, and I'm sure there is a committee which is working on it, but this IIT Roorkee is presently the spearheading it, I would say. So there's a lot to come, and we are looking forward to all the youngsters to take us forward.
Yeah, sure, sir. So Mr. Sanjeev Bumb, he is asking a very, I think, very relevant question for nowadays, that what is the significance of using precast concrete in tall structures, and in what parts it can be used, like tubes?
Well, for example, precast concrete or even steel beams, even when you have a concrete building, concrete structure mainly, these can be very usefully, they can be made use of as far as the slabs are concerned. We don't put it in the outer periphery. If you are talking about the type of buildings that Fazlur Khan made, and if we take that as a standard, then you should put your ideas about precasting on the floor slabs.
Yeah. So, which is better stability on column? Just a minute. people are actually continuously putting questions, so that is being lost. What are the effects of temperature on the tall buildings? Is there any particular effect?
Yes, as a matter of fact, temperature is a important effect. If you really look at it, the sun may be shining on the building only on one face at one time. Now that face is going to expand because the temperature is going to go up compared to the interior of the building and on the other sides which are under in shade. So this creates a lot of problems in the design. So you have to consider that one face of the building, for example, like I explained, is at a different temperature compared to the others. So temperature effects are very important to be taken into account in tall buildings, especially. You should see what is the deformation at the top. At the bottom, you are saying that the entire building is at the same level, and so it is fixed. But when you go up, let us say to the apex of the building, all the temperature effects are felt there. That is where the maximum temperature deformations will happen and the building will grow there. So all this has to be taken into account in the design. It is not only using the computer, my young friends, especially I want to tell you, you have to imagine these things before you have to tell the computer what to do before the computer does it. It doesn't know all this, that the building is maybe heated from one side. You have to tell the computer, okay, it is heated to that extent. Tell me what are all the effects that will happen in the building.
Yes, sir.
Right.
So
Maybe one last question you want to take?
yeah, I think there are more than 200 questions, so we really feel challenged with question to take. This question, sir, just a minute. Do steel buildings pose a fire hazard? And so, is it better to use concrete instead of steel?
I think I have a special section on concrete versus steel, but you have rightly pointed out steel by itself, you cannot have bare steel. You have to cover it with something or the other, some fire resisting material, insulation. So from that point of view, yes, concrete is a better choice.
Yeah. So I'll take one last question in this session. What is the Abbas Alvi is asking? What is the scope of BIM softwares? Are they replacing our traditional softwares like START and ETAP? And which is better, Tekla or Revit or any new BIM?
What was the beginning part of the question?
What is the scope of BIM softwares? Are they replacing?
BIM. You see, BIM software, including all this Tekla and Revit, etc., it comes under the category of building information management. It's really telling you things like in 3 dimensions where everything is. It's not that the structural engineer makes his drawings and the architect makes his drawing and the air conditioning ducts are shown in some MEP drawing. It's not like that. Everything has to be put on one platform or one on one drawing. For example, if you want to see that your pipe is going through one of the beams, you will never be able to make out that if you've got separate drawing for plumbing and separate drawings for the structure. So this is to even find out clashes of between various disciplines who are working, and it's so important to know, what are the various disciplines who are working with you, with whom you have to coordinate, and this is more or less forcing you to coordinate. You cannot have separate drawings architecture, separate drawing structure, and separate drawings MEP. It should not be like that. Finally, even if you make it like that, it has to come in on one platform. And when you are talking about these type of softwares, you don't really make it, you make one model and you enlarge that same model. You don't make separate drawings and then you try to make a BIM model out of it. That is the wrong way to go about it. That is what is happening in many cases today, because it is in the contract that the client wants a BIM model. So all the 2D drawings that we have been making on various disciplines, then we are trying to put it in BIM model. It should not be like that. It should be just the opposite.
For sure. And I think talking from personal experience, I'm sure you would have faced this issue as well, Professor Tandon, that if it starts at one office, the issue really is that of training, right? Across all of the different, um, MEP consultants who are working on the same projects, for everybody to have the same level of training and for everybody to have the same level of expertise on that software is what is becoming a widespread challenge for practitioners. So with that, I will stop sharing of my screen and I will invite you to continue with the remainder of your presentation.
So let's go to the second part of this presentation. And we are going to talk about loads and load effects. We have talked about horizontal loads, but let's go a little deeper. And since there are architects and many other people that I know of as participants, we will try to make it less technical and more common sense. And the second part, part two is really Burj Khalifa and beyond. So what are we thinking of? What was Burj Khalifa? The famous building, the tallest building in the world. And what is going to happen beyond that? So load and load effects. Gravity loads, you all know, is the vertical loads. Thanks to this gravitational force, they give you, you have to take care of them. But for when you come to tall buildings, there is wind and earthquake that you encounter in the design. And those are more tricky than the gravity load. So let's talk about wind. Now, if you have a tall building, for example, here, and this is the wind direction, there is, the building is put into motion because there is such a lot of load and pulsating load. Wind is a pulsating load. I don't want to talk too much about the wind, how its mechanics, but it is a pulsating load, you will understand. So along wind, you can have a motion, and you can also have a motion which is across wind, and you can also have a torsion of the building. That means that the building may rotate also. So these are the major, as far as structural engineers are concerned, these are the things which we have to bother about. And if you look at the elevation of the building, the wind will naturally be stopped here and there will be some eddies which will be formed here. And if you look at the plan of the building, here also the wind will have to go around it. And since this is an obstruction in the wind, you are going to get eddies around it. I mean, this is the nature of any fluid, whether it is gas or liquid, that if you put some obstruction in its path, then it goes around it and forms eddies. So this is the nature of it. And let's go a little more deeper, not too much, but at least a little more. Now, the wind force, why these tall buildings are always narrowing down as you go on the top? It is because the wind force is proportional to the area. Of course, it's proportional to the pressure of wind, but also to the area on which it is acting. So if you can reduce the area as you go up, it is of great benefit, because it is the top of the building or near the top of the building which has the maximum lever arm, and maximum bending moment will occur because of this. So if you can somehow plan buildings like that, and I think if you go beyond a certain height, you will see all buildings are like this. There are exceptions, and I will show you one. But most of them, if you give it to a structural engineer, he will make a building like this. If you give it to an architect, you never know what you are going to get. So here you can see how the wind is going across and how the eddies are being formed. Now, you can see if you round off the corners, it makes an effect. You can, also, you can increase the roughness of the outside. And this has got a tremendous advantage. And I will show you that in due course when we talk, while we are progressing with wind. But if you want to reduce wind effects, surprisingly, the surface roughness will help you. Now, surface roughness, when I say will help you, there is an along wind component, which we also call drag, and there is a crosswind. Now, a crosswind are the most dangerous and most difficult to tackle. In that, it helps you if you have a rough exterior. Now, let us see this thing. We have been talking about it. Are you able to see this building, which is a circular building, which is going back and forth? So this is called the along wind motion of a building. And here's another one where the wind direction remains the same, as you can see here, but the motion of the building is in perpendicular to the direction of the wind force or the wind direction. So both these happen simultaneously on any building. The only thing is whether these effects are serious or not. For tall buildings, definitely they are very serious. I want to talk a little bit about this across wind motion, which I showed you. There is something called critical wind speed. Depending on the stiffness and other characteristics of the structure, its shape, and so on, there is a critical wind speed at which this thing happens, this across wind motion. It doesn't happen when you cross it, and it doesn't happen before. But what you have to worry about is you are going to design in any case for the along wind component. When you have this along wind motion, of course you have to design for it. But when you're talking about the across wind, this critical wind velocity at which this phenomena happens, which means that the building starts moving perpendicular to the direction of the wind, if that is within what can happen at the site, every site has got the maximum wind velocity which you can get from wind maps and so on and so forth. But supposing your critical wind velocity is lower than that, it means that even before you reach the along wind capacity, you are going to have to provide for this across wind. And this is happening in almost all tall buildings or structures, even chimneys. Many of us learnt about this phenomena when we were designing chimneys, that there is something called a crosswind, and it is so dangerous and it is so difficult to eliminate. So this we have understood, people who have been designing chimneys, and then of course, when we came to these tall buildings, the same thing happens there. So we will talk about that. So what is how to find out what are the wind, especially this, the across wind. You see the codes, we have got a wind code IS 875 part 3, which is specifically on wind forces. Now, along wind, they give you a lot of data or a lot of design guidance. But as far as across wind is concerned, we know about a crosswind only for the simplest of cross sections. Like if you have a circular section, which you find in a chimney, or you have some kind of a square. Yes, some guidance is available. What is going to happen in the a crosswind, when it is going to happen, how to find out the critical wind velocity. So if you have a slightly more complicated issue, then you go to what is called a wind tunnel testing. I hope you've heard of a wind tunnel testing. I mean, that is where you put a model of the actual building to a small scale, maybe 1:100 or something like that, and put it in the wind tunnel and see its behavior. And you can find out there is something called a Reynolds number and a Stroud number, by which you can make sure that you are modeling the structure to a smaller dimension, and still getting your results. So that is what the wind tunnel testing involves. That means that you, like in all models, when you make at a different scale, you have to obey certain norms. So the same thing happens even in wind tunnel testing. So, for example, the Eurocode says that for slender buildings, that means the height to width ratio is greater than 4, then wind tunnel studies are necessary. If distance between buildings are less than 25 times the dimension of the building, again, you have to do a wind tunnel testing of that particular building. And there is another one that when your period of motion of the building, and there are it's easy to calculate what is the period of vibration of a building. So once you get a period of vibration of the building less than 1 hertz, 1 hertz means that one full cycle per second. Once your natural frequency is less than that, or your time period is more than that, any one of the frequency is the opposite of 1 over the time period. So if you can look at it as a time period, or you can look at it as a frequency. But if you are not meeting those requirements, then wind tunnel testings are obligatory. And I think that most of the tall buildings, we are talking about time periods of, say, 6 seconds, 7 seconds. Now, if you say 1 over 6 or 1 over 7, it is going to be less than 1 hertz. So in these type of cases, wind tunnel testing is absolutely essential. This is the World Trade Center, built in 1973, and of course it lasted till 2002, and I think everybody knows what happened to it in 2002. But the important issue is that this was one of the first buildings that people thought of testing in a wind tunnel. Now these are the World Trade Towers, the 2 towers of World Trade Center, and you have the surrounding terrain, because when wind is blowing and it is blowing across this disturbance that you have created on the windward side of the building, it is going to create some eddies or some disturbances which are going to act on the structure itself which you are testing. So there is no use testing only the building by itself. You must also test it with the surrounding terrain. And incidentally, this is always put on a turntable, a turntable, because the wind fan or the blower is only at a fixed location, and it can blow wind only in one direction. So, but you can turn around this turntable and make sure that you are you are also seeing if the wind blows from any direction, what are the effects? So this is something which is quite normal. And so now what do we do? One is that, as you see that, these regular formation of eddies, we also call them uh, uh, one Carmack eddies street, as a matter, because it's almost like a street. The person who first talked about it was von Karman, and he said that, okay, so this is forming. Now, what should you do about it? The best way is to disturb the flow. So I remember I talked to how the outside of the building surface, you should make it rough, because if you make it rough, you are getting out of the major problem that you feel that you are going to face in wind engineering, the structure, that is the transverse wind. Of course, by making this surface rough, you are increasing the along wind effects, but more importantly, you are reducing the transverse wind effects. Now, you look at this building, for example, this is in Shanghai. They made this opening here in the building right at the top, so that here the wind is disturbed, the pattern is disturbed, and it doesn't form a sort of a lock-in kind of a situation where it starts moving in the transverse direction and keeps on moving. So as you can see here, this is all done. Maybe the architects have a role to play also, but the structural engineers like it very much, and they are in sync with the architects as far as making some kind of a pattern which can disturb the flow of the wind. Okay, let's talk about earthquake, which is the other big lateral force. So how safe are the tall buildings during earthquakes? That is the question which people often ask. So during an earthquake, the ground is subject to severe shaking, and the predominant period of shaking depends on soil conditions. For example, the period may be very small if you are in rock, but if you are in soil or loose soil, then the period of vibration becomes larger. So it says here, for a rocky ground, the fundamental period may be around, I can't see what is written here, but anyway, 0.5 seconds. And on the other hand, for soft soil, it may be 2.5 seconds. Now, we have already talked about how the buildings are put into vibration when you have a force acting on them. Now, earthquake is quite different from wind. In wind, the wind force is acting actually on the structure. What happens in a tall build in the case of an earthquake is that it is really the ground which is shaking, and because of the mass inertia of the building, it is put into motion. So the two phenomena are quite different. Wind and earthquake behavior is very different. So once you have there is an earthquake and the earth shakes and the building is put into motion, the question is what happens next. Now, if you want to calculate roughly the period of vibration of a tall building, it is about 0.1 times the number of stories. So you take 3.5 or 4 meters as the story height, and you know the total height of the building, so you can roughly calculate what is the number of stories. So 0.1 times the number of stories. So if you have a story height, for example, of say 100 meters, then 100 into 0.1, which means 10 seconds will be the period of vibration. So this is how we do it. But if you really look at it closely, that it's really between 0.5 and 2.5 seconds that we should really be worried about. Of course, if the soil is very weak, it may go up to 3 seconds also. These are only figures so that we can understand them. No tall building is in the range of 0.5 to 2.5 second. When we are talking about tall buildings, super tall buildings, mega tall buildings, in that category of buildings, you don't get a period of vibration which is so slow, so small. So since they can never get into resonance, that means the period at which the earth is shaking and the period of vibration of the building, if they are in resonance, then you have a big problem. Then it will just keep on increasing till it collapses, the building. Or you have some other means of reducing the effects of earthquake. So I think if you let's go forward. I think earthquake phenomena, you have understood how it happens, why it happens, and why, since the period of vibration of the tall buildings is high, it is long, therefore by itself inherently it is safer than a shorter building. You should be worried about buildings which are between 5 and 25 stories. They are the most vulnerable during an earthquake. Now there is another thing called damping. Now, if I'm sure all the structural engineers at least know, see, this is what we call a response spectrum. This shape, that means that this is the period of vibration and this is the acceleration that you will generate because of the earthquake. So the more damping that you have, and we will see how to create damping, but if you can understand this properly, if you increase the period of vibration, the earthquake force or the acceleration, as you can see, is always reducing. If you are in this region, let us say you are at half a second, then you have got an acceleration which is the maximum. But if you have got something like 2.5 seconds, you are somewhere maybe about what, 1/2 or 1/3 of that. So the longer the period of vibration, the safer is the building as far as the earthquake forces on it are concerned. Now damping, there are various types of damping. There is the structural material damping. There are structural connections, if you have any. There are foundations which create damping, non-structural components, aerodynamic damping. So all these various types of damping are there. But what we are going to talk about is that these dampings may be there already inherent in the structure. What is the other thing that you can do? So before we come to that slide, I just wanted to make one more slide about concrete versus steel, because this question has been asked also and people are asking. Concrete buildings seem to be better because they are more stiff. That means stiffness means that the deformations are small, because these tall buildings are really, their design is governed by what is the acceleration, what is the deflection that you have at the top of the building, so that people there don't feel dizzy. So from these point of view, concrete is better, and of course it has got an increased fire resistance. But is this the final word? Concrete these days, you have high strength concrete which has further benefits like less floor area is occupied by columns, modulus of velocity, which is of great help. If you have high strength concrete, modulus of elasticity increases and there is less deformation. And there is early decentering of slabs is possible. You remember Empire State Building, 4.5 floors per week they did. We are talking about in a concrete building 4 or 5 days per floor. That is how the difference is. So, but it is still early. That means that the concrete at 4 or 5 days old, it is, if you've got a high strength concrete, you can decenter it because it has got enough strength to take its own load. So what determines the earthquake resistance of a building? Only how well it is engineered, not the material, not steel nor concrete. It has got some advantages, disadvantages, that's all. In Japan's Kobe earthquake of 1995, it was shown that the collapsed buildings were about the same, 5% in concrete and steel. So there is, in actual fact, there is nothing to sort of select from concrete or steel. There are other issues which you have to worry about. For example, the costs, etc. Those are more important considerations than which come into consideration rather than what is safe. Both are unsafe. Now let's talk about how to reduce the effects of the building. We talked about that chart, if you remember, damping. As you keep on increasing the damping, the force decreases. So I'm going to talk about only one type of what is called assisted damping of the structure. So how do we do it? This is the famous Taipei 101, which is in Taiwan, and it held the world record for a number of years. It is 509 meters tall, and you can see there is no narrowing of the building as you go at the top, because they wanted to represent a bamboo shoot. So a bamboo looks something like this. So this is what they wanted to present. So irrespective of what the structural engineers want, there are other considerations which come into the picture, which the architects know more about than we do, as to what should be the shape of the outer building. But here also you can see that despite all this, they have put a lot of roughness they have introduced on the outer skin of the building. At the top of the building, they have got a steel ball which weighs about 700 tons. This is hanging from inside the building. So this part of the building is wasted as far as its occupiability is concerned. But it has got great benefits because this is called a tuned mass damper. A tuned mass damper means that it moves in a direction. This is suspended, remember? It moves in the opposite direction to which the building is moving. So it is slowing down the motion. And this building, for example, has been designed for a return period of earthquake of 2,500 years, and it is designed for a 216 kilometers per hour wind, and its cost is about $1.9 billion. Okay, let's see how this functions. Let me see. Are you able to see this? If you see carefully what is written all over the slide, at the top it is movement of the TMD, the tuned mass damper, which is this huge steel ball. It is moving opposite to the direction of the building, which is shown in blue. So it is slowing down the motion of the building when it shakes, whether it is during earthquake or during wind. It is dampening the effect. So this is something which is extremely important. Okay, let's talk about the last part of my lecture, which is Burj Khalifa and beyond. This is the Dubai Creek Tower, which you may not even have heard of, but it is 1.3 kilometers tall, and it's done by the famous architect, structural engineer, and sculptor, as he calls himself, Mr. Santiago Calatrava. And the developer is MR Properties, and Dubai Creek means you know where it is located, and it is a tall single tower, and it even, as a matter of fact, part of it is bigger. So, and the rest of it is of the same dimension till you come to the ground, but it has got uh, steel cables, as you can see here, the steel cables to stabilize it. So it is a not a uh, self-supporting building. It is a supported building by whatever means. In this case, by steel cables. So you can see here, and if you can, I don't know whether you can make out, but this is what the building is going to look like when there is a mall nearby. This is what it looks like from close quarters. You have the mast which is going straight up, and you've got these steel cables which are anchored to the ground. Uh, so Calatrava is known for his spectacular designs inspired by natural forms in movement, undulating waves, trees bending in the wind, flower petals opening, you name it. He has got everything. He has made it into buildings. So the problem is that this will never be a world record. Why? Because the Council of Tall Buildings and Urban Habitat skyscraper requirements are that it should be self-supporting and 50% of the height should be occupiable. For example, if you just make an antenna at the top, that is not a building. More than 50% should be habitable. At the moment, the multi-layered pile cap you can see here, this is the a hole in which this huge tower is going to be placed inside, and it is going to be stabilized. So it is the pile cap itself is made in several layers, as you can see. So it is end of 2017 or beginning of 2018, it was like that. It still remains like that. The rest of it is not being made because all these tall buildings, they can run into problems. Finances being one of the problems. And Calatrava's buildings, they always overshoot the budget. So if the people who appointed him didn't know that, then they didn't appoint the right person. Here you can see from some angles, it looks like a desert lily. From some other angles, it seems to look like a rocket ship. But unfortunately, this is where it is at the moment. Okay, let's go further. What are the other things that we can talk about? The 2-mile tower building, which was visualized by an American architect. I think the Americans are pretty good at visualizing. Like Frank Lloyd Wright thought of the first mile-high building, and there is an American architect, Eugene Sui, who made a 2-mile high building concept. And he says that if you want, you can have the entire San Francisco, whose population is 8.83 lakhs, can be accommodated in this. So I want to ask, and of course, you are maybe occupying about 1.8 kilometer at the bottom as the diameter of this tall building. And of course, you can see the shape. It is reducing as it goes up. So this is how all the buildings are made normally. Okay, so this is interior area of floors is 1.140. We no longer talk about square foot businesses here. which the builders in Delhi are fond of calling. Square kilometers, 140 square kilometers is the area of the building which is occupiable. Okay, one more last slide. What about there was in 1995, Taisai Corporation of Japan, they are huge contractors. They made a concept of a building which would be 4,000 meters tall. And that concept has not yet been realized. And thank God it's not realized, because you can solve all the engineering problems. You can make something which is 4 kilometers tall. The question is, who's going to live there? What about the altitude sickness and fire hazard and elevators? Three things have been identified as why this building cannot be made, although it was conceived in 1995. I'm sure that you people have been to Ladakh, which is at an elevation of 3,000 meters above sea level. That means it's 3 kilometers above sea level, and you require time for acclimatization and so on and so forth. Here, we are talking about 4 kilometers tall. Unless you are willing, of course, I don't know, during this lockdown, people have to wear masks, and they have got used to it. But here you have to wear oxygen mask before you can live there at the top. So it's not that simple to make. Engineering problems, yes, you can get out of it, but these other issues come into the picture. Okay, thank you very much for your kind attention.
Yeah, thank you very much, sir.
Yeah, okay. Okay.
Yeah, thanks a lot, sir. I think we can take very quickly. We can take few questions. We have got on board almost 384 questions. So, and there are some questions I'm seeing there people are putting on chat also. So, what I will request all the participants is please, we'll not be able to cover the question, definitely all questions. So, you please log into the Concrete Club app, which Priyanka has already told, and you can put there these questions. We are, putting the topic wise, speaker wise sessions, and the questions will be there. And we'll be requesting Professor Tandon. He will be, gradually answering those, and those answers will be posted on that wall. So just to take up some questions, Engineer Jitendra Ambani, he's from Mumbai only. He want to know that for the tallest, the design, is there design of mega tall structures which you talked about using segmental construction technique to what height maximum? Any examples?
No, we don't use segmental construction in buildings, really. It is something which we do in bridges, which are not so tall, and it is possible to. The main problem of segmental construction is that you have to transport the segments, you have to erect them, and if the segments, if that becomes unviable, then you can't use them. So even in bridges, we carefully examine how particular segments are going to be brought to the site, how they are going to be erected. All this is a major issue. So in buildings, rarely you see a thing like that. The only thing I can think of is that people have made bridge piers, which are also vertical. If they are not too tall, they have used segmental construction in that. That means that they are the segments are put one on top of the other. It is pre-stressed, that complete height, and then you can use them as piers. But that is, again, not very common. But the superstructure, yes.
Just a different kind of question. Just I saw in the chat box that somebody asked that is there any significant effect of rain over the tall structures, especially the upper part?
You see, if you really look at it, the wind velocity which is going to happen at the top of the building is going to be enormous. I think if you have gone into aircrafts and you've seen the pilot's cabin, there is a bulletproof glass, thick glass, which constitutes his, the windshield. That is because the wind pressures and forces at that level are very high. And of course, there is also the question of relative motion. So the motion of the aircraft has to be added to that of the wind. It's becoming even more complicated. But when you are talking about, being at 1 kilometer high building, you have to make pretty certain that everything is firstly airtight.
Yeah.
The glass panel firstly can, of course, it can resist it, and our new national building code, which was published in 2016, has got a chapter on design of glazing. So the glass that you require, at that level, in any case, has to be made completely watertight. Watertight means airtight. It has to be made. And so a properly designed building should not have a problem like that.
Yeah. There is one more question which is relevant, I think. Just 3 days before we had a session on ultra high performance concrete. So there is a question that what is your perspective, sir, on use of ultra high performance concrete in the tall structures?
I think that is definitely the future. If you really look at even the Burj, the concrete strength used there was less than M100. It was something like M80 or something like that, M80, M90, somewhere there. So it had not even reached M100. People are talking about M150 these days. So the big advantage of this high strength concrete is that the modulus of elasticity of concrete is very high at that stage. It is the modulus of elasticity is proportional to the square root of the strength. So it's quite high. The higher you make it, the lesser the higher is the stiffness of the building, lesser is the problem of acceleration and deflections at the top. So it is of great benefit. And I think in future you will see buildings which will be made from this ultra high strength concrete. And of course, this word one should not use. Is the high performance concrete is the correct word. The high performance concrete means the performance may be due to for any reason. For example, Burj building has been made in the most adverse environment, high temperatures, high humidity, salty kind of a air. You cannot have anything adverse than that as far as corrosion is concerned. So the prime objective there of a high performance concrete means that it should perform the primary purpose or primary objective of high performance should be that it should not allow corrosion to happen, because if it happens in a building which is that tall, it is a disaster. So high performance concrete, and sometimes you require high strength along with high performance of a certain kind. So this is something which you have to decide.
Yeah, definitely, sir. And I think high performance concrete nowadays, not only in the mega tall or super tall, even in the normal buildings also. I mean, it is required, but definitely more adoption is required, as, like you said, because we are in a position to produce even SEC RMX. We are producing M150 kind of concrete, and we are supplying in some projects in Mumbai. So now this is the last question. It is not a question, just your comment on, in a general scenario, people are asking that what is your perspective, how this tall structure thing and this concept will move in India, and what are the challenges which are, in India, structure consultants and engineers are facing for building tall buildings?
I think the biggest challenge that I see as far as consultants are concerned, you asked?
Yeah, consultants, engineers, architects, all the fraternity.
Well, I think maybe at least engineers, I'm sure of, architects to some extent. The Today the building industry is being run by developers. It's no longer that the owner who has got a small little flat in the whole uh, development is has anything to do with the appointment of the structural engineer or the architect. It's the builder who is appointing them, these professionals, which is the wrong thing which has happened in our country. Because what happens is that the main objective of any builder or any businessman is to make money. It is not that it should. Rarely you find somebody who wants to make a super building which looks nice and all that. If he's a rich person, he will be able to do that. But when you have got, you know, 500 people living flats in a building, they want to make it as cheap as possible. And what they don't realize, the builders, is that by reducing the fee to a minimum of the consultants or architects, they are not going to reduce the the cost of the building. The cost of the building is going to go up because the prices that they are paying for designing the buildings has come to a stage where only incompetent people or who got no other work would like to get into it. Of course, uh, there are still people who are getting into it because we are consultants and professionals and we have to get work. But really speaking, it is that is, I feel, the most dangerous thing that has happened to the building industry in our country. There are no norms by which you fix fees, etc. It is just you give a fee and they say so many, and they are still working incidentally in square foot. They are saying so many rupees a square foot is the fee. That's it. Even the amount of steel that they are putting in the building, that is another danger that I find, especially for structural engineers. They are used to what they had heard when they were, these builders, or they have what they have inherited from their uh, earlier generations. How many pounds per square foot should a building have as far as reinforcement is concerned? They are still in that, what is it called? Sorry, I don't know whether that was the question which I am answering, but these are some of the dangers which I feel are happening, that people don't know. The developers are neither know nor they are wanting to know what are the new codes of practice, how the code has changed from, let us say, 1967, when maybe you could do so many pounds per square foot. Now there is so much of things that you have to do if you want to do a building which is properly designed, which will stand in the earthquake. The earthquake comes only once in 500 years, let us say. That is the return period of the earthquake for which buildings are designed. So maybe during our lifetime, or during the builder's lifetime, that earthquake will not happen. Some small little shakes will be there, for which even the building which has been designed only for vertical loads will stand. But if you really have a serious earthquake, what we call as a design basis earthquake, half the Delhi will be floored. That is what is going to happen, including the buildings which are the so-called reinforced concrete buildings which we are making with so much of money and all that is going to disappear. So let's hope
Yeah,
that our lifetime, at least 500 years, has not yet come. But the danger is that when you say return period, it can happen tomorrow, or it can happen after 500 years. I mean, this
yes,
range of periodicity is available. So when you are making a building, You have to really design for a 500-year return period. That is what the code says, or at least whatever it implies, not says directly so far, but implies that. So I think that those are some of the biggest dangers which I have pointed out uh, in the building industry today. But being professionals, we are excited about the technical challenges. Even though we may go broke by the end of the project, we are still excited about what we have been able to achieve in that uh, short span of time. The enjoyment that it gives,
Yes.
I think, is perhaps worth
No,
all
very
the
well
fees, reduction, etc.
Mr. Tandon, your passion comes through clearly
very,
in both your speech and
yeah.
everything that you share. I'm afraid we have, in fact, overshot our time, and
Okay.
I would. There's so many questions and so many of you who sent in most of your queries. Unfortunately, we have to
There are
close
more
the
than
debate.
500 questions. So I think we already briefed and people here they understand. I mean the limitations of this the online webinar. We already had more than 2,200 people at the beginning, 2,300. So anyway, we will be definitely addressing these questions. We will take up these questions in our Concrete Club app. You can always log in. You can go to Play Store and apart from this session, you will get a lot of other coverage of other sessions also along with the Q&A. So now I think we will come to end of this question answer session, and that was a very wonderful session by Professor Tandon and all the people here. I once again thanks, and now I am just handing over to Priyanka for her closing remarks and some one or two slides. Priyanka.
Thanks a lot, Moin. So before we conclude our session, I would like to take 5 minutes more of your time, participants, and let you know about the Concrete Club that we have been talking about. It is a network of construction professionals that we have created. It is a place where we want you to come and add your experience, add your expertise, ask the questions that you need in order to improve the quality of the building and in order to improve the construction for the country. And I think this is a purpose that is bigger than us. So one of the sections that we're talking about over here, as you can see, is the discussion forum. It is a place where you can take the questions that you have found and raised today. Feel free to raise these questions once again on the discussion forum. We will be keeping track, and we will try to get Mr. Tandon and of course other experts who are on the platform to answer your questions. Following the discussion section, this platform also allows you to create your own portfolio. And we found that there are so many engineers, architects amongst us who are doing great work, but don't have necessarily our own websites. Here is a space which allows you to create that website of your own and also to share it on different social media. So I would encourage you highly to take this for a spin and increase your reach. And this is a section that we are in fact really excited about. In Mr. Tandon's approach today, we saw how he brought in so many technical, personal, professional aspects in. He brought in aspects about design and architecture, and he brought in aspects about engineering. And this is what we encourage you to share on the inspiration zone. It is really what about building inspires you, and how can we inspire other upcoming professionals to take that learning. Can you take learnings from Santiago Calatrava? Can you take your learnings from Frank Lloyd Wright? And what would you like to share on this particular space? Make that into a post. It can be your personal work. It can be that of an engineer and architect that inspires you. So with that, I come to a close on the Concrete Club. I leave you with this knowledge of the Indian Concrete Journal, which most of you would have found the questions while you were registering. The Indian Concrete Journal is in fact older than ACC itself. We've been around since 1927, and we have been on the Indian Concrete Journal talking about better building practices. It has been traditionally a research journal, and it has been inviting a lot of you researchers and a lot of experts to take in that technical aspect. Now we are opening up a second aspect to it, which is what you see on the lower left hand side of the screen, which is the Indian Concrete Journal online.com ICJ Professional. The ICJ Professional encourages you to share case studies of your work, which are examples clearly of better building. And as I had mentioned earlier on in this slide, what does better building mean for you? It could mean better workmanship, it could mean better engineering, it could mean better technology. And we'd like for you to share these outstanding case studies and examples with us. So we highly encourage you to contribute to this particular website. With that, I'd like to close this session and thank once again Professor Tandon. You have been fantastic, and as I had said, it was, while the topic really was tall, mega tall structures, we saw so much of your personality, of your work, and how you see this profession. Your passion came through, and clearly the audience could see that as well. And we thank you very much for being a part of this ACC Knowledge Series. We hope that we will continue to engage with you in the future through Concrete Club and our other initiatives. I thank Muin as well for conducting the moderation session and for joining me. Muin, would
Okay,
you have
thank you, Priyanka. Thank you, Moin. It was very enjoyable being a part of this series.
Fantastic.
Thank you, sir. Thanks.
Okay, thank you.
Thank you,
Thanks,
everyone.
everybody.
Thanks and goodbye.